My name is Tobias. I'm going to talk to you about Dynamic Programming 101. I've done this talk a few times before, and people have come up to me saying, hey, why is it named Dynamic Programming 101? And for those who didn't know, 101 is basically the introduction course. Like if you go to, if you study in America, you have Economics 101, like it's the first course of learning economics. So that's what I'm going to do now. I'm going to try to explain the basics of dynamic programming. And I believe that web developers only care about printing out HTML as quick as possible. We don't care about fancy algorithms. So I want to show you there's more to programming than printing stuff really quickly. That's the setup, and I hope you're all buying into that. And sorry. If you haven't seen me talking before, I really need you to give me some visual feedback. So if I say something, you nod, and if I make a joke, you laugh, and stuff like that. Excellent. Anyhow, short about me, I work at a company called Happier. We're matching people and companies together on soft skills. I do plenty of Symfony stuff. I run PHP meets up in Stockholm, and I also work with open source. I started my open source career like in 2015 on a conference like this. PSR6 just came out. So me and a group of friends, we're like, hey, let's build implementations or bridges between Doctrine and PSR6. And after a while, we're like, why don't we implement this ourselves instead? So we implemented a lot of storages and made them PSR6 compatible. And that's PHP Cache and PHP Cache Bundle. At the same time, I'm starting to be interested in HTTP Plug, which basically is an abstraction over HTTP clients. You've probably heard about these before. Excellent. Doing HTTP clients, you do a lot of API clients and do a lot of mail clients. I even wrote like, this is how you should write your API client. And currently I'm maintaining both Guzzle and Buzz. I written my own PSR implementation that is super nice and quick or whatever. And geocoding stuff and plenty other things. The cool thing here, the cool library, is the NSA library. NSA totally violates all your class privacy. So accessing private properties or private methods, it's no problem with using NSA. And why? It's good for testing, maybe, I don't know. Anyhow, I contribute to a lot of other stuff as well. But this is where I am. This is the things I like to do. Let's get started. Whenever you're faced with a problem, I assume you automatically start thinking it as a smaller problem. Consider the problem of getting to work. I mean, you got to figure out what to wear, you got to figure out what to eat for breakfast, and you got to figure out how you actually get there. And when we're talking clothes, like what trousers will I wear, what sweaters will I wear, and you're trying continuously breaking this up into smaller and smaller problems. Same thing building a website. Like you got to figure out, sure, what's the design it's going to have, what data models, what views, and when you figure out the data models, how should you store the data models? Like are you storing in MySQL or NoSQL? I mean, this is called divide and conquer. You probably all know about it. You do it automatically, right? I mean, you do it without knowing. And yeah, I have fancy animations showing you divide and conquer. The thing with divide and conquer is, if you're trying to be more like computer scientist, divide and conquer may lead you into recursion, right? This is the weak link in my presentation, so I need you to say, yes, the recursion is great. If you don't know recursion, this is pretty much it. This is two pieces of code. One writes, they both calculate factorials. Factorials for number 4 is 4 times 3 times 2 times 1. And on this side, I have an iterative way of doing that. I just take the number and multiply it and repeat, normal loop. Over here, I'm doing it in a recursive manner, which actually, recursive basically means that the function calls itself. I hope this is familiar to all of you, or everybody understands this. What is not as familiar, it's when you are a computer scientist, when you're talking about computer science, there is a rule that you cannot talk about recursion without mentioning this guy, right? This is Fibonacci, you have to mention Fibonacci number. Fibonacci was a mathematician, lived in the 1100 something, he's from Italy. Fibonacci has nothing to do with the Da Vinci Code. There was actually one candidate who applied for a job who claimed he loves Fibonacci numbers because he read the Da Vinci Code. Anyhow, This is a great Fibonacci sequence. And as a short reminder again, a Fibonacci number is the sum of the two previous Fibonacci numbers. So if you like my nice animations, this is how you calculate Fibonacci numbers. I'm sure everybody knows this. And in code, if you're doing recursion, it might look something like this. So I get Fibonacci number for 5. If it's less or equal to 1, then I just return the n. And if it isn't, I calculate Fibonacci for the two previous numbers. And this will automatically spits out a Fibonacci number. Make sense? So if I ask you now, what is the Fibonacci number for 15? Sure, 14 plus 13. And if you're looking at my nice table or my nice list, the 15th Fibonacci number is 610. Excellent. Quite easy to see and give me that answer. I hope. This is more math. So what if I change my question now? What is the Fibonacci number for 1002? It's big. Any other suggestions? It's very tricky to find out. I mean, this is a huge problem. This is quite complex. But what if I helped you? What if I told you the Fibonacci number for 1000 and 1001? And now asked you, hey, what's the Fibonacci number for 1002? You will say x plus y. So if you know the answer to smaller problems, it's easy to figure out the answer to the big complex problem. That's a point I want to make right now. I want to refer back to this later, but keep that in mind. I want to dig into more Fibonacci code now. This code is not complex, but it's worth studying. As you can see, we do plenty of calculations here. If I say, let's call Fib5, I call Fib5, and that in turn is called Fib4 and Fib3, which in turns call plenty. As you can see, I do a lot of repetitive calculations. Like I call Fib2 3 times. And if I maybe could save the answer for Fib2, that will be more efficient. So let's rewrite my code a little bit. I'll have a nice class here and write something like this. So I use a cache, and if I've seen the calculations for Fib5 before, then I just serve the cache. If I haven't, I'll actually do the calculation. I call it cache. I mean, if a computer scientist will say memorization, but it's basically a cache. So the main thing about dynamic programming is that we can divide the big problem into smaller overlapping subproblems and be smart about and saving the calculations for these subproblems. You see and understand the code? Then I'm going to move forward to my, So you have a big problem. You can create smaller overlapping subproblems and store the calculations. So this is with Fibonacci without cache, or without memorization, without dynamic programming. And we want to do Fib5 with, I reduce a lot of calls. And if I do reduce a lot of codes, then the execution will be quicker. In fact, if I do Fib500, I remove 99% of all the calls. Which, if I told you I have an algorithm that's 99% faster, then you obviously would be interested, right? So now we've basically done hello world of dynamic programming. And I want to introduce you to the more fun stuff. Do you feel confident about this introduction? Great. I haven't left anyone behind. Everybody's with me. Everybody understands it so far. Because the more fun stuff is obviously graph theory. And the first thing you need to know about graph theory is that these are not graphs. These are maybe charts, these are maybe diagrams. You can call them whatever you like, but these are not graphs. A graph has a node. A more interesting graph has 2 nodes. And nodes can have edges between them. An edge can be either undirected or directed. And an edge can have a weight. This is a full-featured graph. And this is an even nicer graph. And the cool thing about graphs is that if you have a problem and can express this as a graph problem, there's probably already a solution to it. because there are so many algorithms working on graphs. So your task, I mean, if I'm your boss and giving you a major task, you should just convert that task to a graph problem, and the solution will be given to you. So let's, for instance, imagine that these are computers in a network, or if I slap on some numbers here, it may be people and how much they like each other, or it may be cities and distances. It can be anything you like, really. And if you're gonna go with cities and distances, we can ask ourselves, what's the quickest route from A to B? Or we can, if there are computers in a network, it can be how much data can you send from A to B? What's the maximum capacity of this? Or if there are people, how much they like each other, it could be who should get married if you're gonna maximize if you're gonna maximize the happiness in this group, who should get married? Anyhow, it's a lot of things, and I'm gonna talk to you about some search algorithms, and let's imagine the problem getting from A to B, and we're gonna discuss a breadth-first search. How many of you know that how many know of breadth-first search? Show of hands. Excellent, it's about 30%. How many of you can confidently implement a breadth-first search right now? Yeah, I mean, I'm with you. I mean, excellent. I gotta go through it. So going from A to B, we can select one node A, and what we're gonna do with the breadth-first search is we're gonna ask all our neighbors. Like first we're asking this neighbor and see what is the distance of getting here. So I write that distance down. Then I go to the next neighbor, write that distance down, and the next neighbor, write that distance down. When I visit all my neighbors, I go to the first unvisited node and checking its neighbors. Click. Yeah, checking its neighbors. And I move on. Like checking all the neighbors, and I do them in turn. And I write down the distance of getting there. And when you've done all of them, you can backtrack with the shortest distance. So you can easily find a path like this. If it doesn't really make sense, I'll show you some code. In my code example, I've removed all the numbers because numbers make things more difficult. The implementation is more difficult. So currently I want to find the path with less nodes. So I have this graph again. I want to find a path with the least number of nodes. So my code looks something like this. I have a list of edges. I have a queue of edges, and then I'm just adding edge. That's not really interesting, so let's look at this thing, the breadth-first search. So what I'm doing, I'm giving a start node and a goal node, and I put the start node on a queue, and I say that I visited the start node. And then, while the queue is not empty, I'll take the first element out of the queue, looking at each neighbor, and if it's the first time he's seeing the neighbor, I store it in the visited line, in the visited array. And then it's just a matter of fact to print this. Sure, I'm trying to see, like, I can move on, right? And then then I just print this, and the bootstrap is just adding all the edges, like you saw. And when I run this, it will look something like this. And as you can see, I have a shortest path of 5. There are plenty of optimal solutions like this. There are plenty of shortest paths of 5 in this graph, but you'll see that my solution doesn't have 6 nodes. And I took the long route on the up, you see. And I hope you're still confident with this. I hope you're still like, oh, this is semi-simple, or I understand this. So imagine a maze, or look at the maze I draw for you. I hope you can see that you can, if we would be working 1 hour, 2 hours on this maze, we can translate this to a graph, right? The number in each box represents how expensive it is to go to that box. So it's kind of similar to the graph, right? And you can see I can translate it for a graph. I choose this representation for the next few slides because my point will be easier to show. Yeah, the number in each square says how expensive it is to get there. So imagine the same question again. I'm gonna start from that node, and gonna end here, and I'm gonna do a breadth-first search to figure out which the shortest path is. I slap on some colors because colors are easier to see and understand. Red is expensive, green is cheap, and let's get started. So I look at the first node, and I discover its neighbors. I take the first neighbor and discover its neighbors, and in an orderly fashion like this. Now it's placed by itself. So I slowly discover the full graph, and I slowly will find the optimal path. And when I'm finally done, and sorry, I do this by hand, so I stopped halfway because I was lazy. I'm sorry, but you get a point, right? You get a point. It's quite slow. That's what I want to make stress as well, because it discovers the full graph. So could we do something differently? So instead of taking each neighbor one by one, could we do something differently? We could do a depth-first search, which basically is I take the first neighbor and I go there, and then look at those neighbors and take the first one and go there, which will look something like this. Oops. It's still quite slow. I still search the full map. And imagine, I mean, this is a 30 square matrix, but imagine if I have a 300 or 3,000 square matrix, it will take quite a long time. So could I be better? Could I do something differently? It was a semi-rhetorical question. I want you to think, and maybe someone would be bold and answer, but you don't have to. But could I be better? I could do something differently, yes. I could do a greedy algorithm. Say, I always took the best possible decision. Like wherever I am now, I'm looking at my neighbors and take the best possible decision. So let's try. I'll go to the ones. And sure, you'll see what I did here. I was tricky. I mean, first it looks nice with the ones, and then I go to the alley of eights, and that's not very. This will not give me an optimal solution at all. This will be horrible for this graph. So I could do something. I could do the opposite. What if I take the worst possible decision all the time? And that's actually on a random graph. On average, best fit and worst fit performs equally well. So, but I mean, obviously, in your company, with your problem, you don't have a random graph. You have a specific kind of graph, and that's why you should try different algorithms. Also, best fit or worst fit doesn't perform better or worse than a random walk. So you can just randomly take the next node, and you'll do equally well. Obviously, when doing something like this, it's really, really quick, because I don't have to go through all the full graph. I just have to go and find a path. But this does not guarantee the optimal solution. I can get any solution. Maybe the solution is good enough, but I mean, currently, we all are interested in the optimal solution at the moment. Also, heads up, when doing something like this, you have to consider loops. I mean, you can get stuck, and you have to avoid that somehow. So let's try to combine these two. Let's try to do something that gives you the optimal solution, but does not solve the full graph. And if you're cool, you've probably heard of Dijkstra's algorithm. And I'm sure none of us are confident implementing it. It's a bit more complex, but the idea is quite simple. Bear with me now. Or sorry, I shouldn't say simple. I mean, sure, it's simple for me because I've spent like 40 hours preparing this. But I shouldn't say simple. It's I should use a different word, but my English is too poor. I gotta move on, sorry. So Dijkstra works like this. I take the start node, I write down the distance, how expensive it is to get here, and then I look at all my neighbors and write down the distance to get there, like how expensive it is to get there. Now I start with the discovered but unvisited node of the lowest value. So I'm currently, I only have 3 discovered nodes at the moment I haven't visited. And which one has the lowest value? It's the one at the top. So I go with that one and discover all its neighbors and write down the distance. And I move on. And as you can see here, this is a neighbor, but I've already discovered this neighbor. And so I can check which, if I write my number over here, like would be a 7, or yeah, a 7, would that be bigger or less than a 5? I keep the smallest one. So here I don't do nothing. And then I move on with the discovered but unvisited node with lowest value, etc. And this will play by itself now. yeah, I guess you understand. And the cool thing about Dijkstra's is that it guarantees an optimal solution, but it does not search the full graph. So if I had an infinite large thing, an infinite large map, I could like have 50% undiscovered, but I still can guarantee the optimal solution. And when this finally is done, you will see here are nodes I haven't even discovered. But I know for sure that these are not part of the optimal solution. And also, again, I apologize for making this graph. I made this graph and like, yeah, I gotta show Dijkstra's, and I only have one node I didn't discover. But I mean, on average, this will be way quicker than, I mean, I would search like half the graph, or not only 98%. Do you feel confident about Dijkstra's, or I mean, not implementing it? I can't, but do you feel confident how it works? So, what if we What if we connect this to Fibonacci? The point I was making with Fibonacci before, Fibonacci for 1002 is quite difficult, like solving Dijkstra's 30 is quite difficult, but if you know the answer for a simpler problem, solving Fibonacci is simpler. So I wanna show Dijkstra's again, but in a different representation. So I start with the first one, and it discovers all its neighbors. And then from here, I start 3 new Dijkstra's. But not Dijkstra 30, but Dijkstra with 29 squares. And then when I solve those, I can just add the constant of 3. So if I move on, now I have 3 Dijkstra's of 27. And obviously, as we know, Dijkstra's of 27 is easier to solve than Dijkstra's of 30. Like the Fibonacci of 1000 is easier to solve than Fibonacci of 1002. But if you know the answer to Fibonacci 1000, it's easy to solve Fibonacci 1002. So I'm solving this Dijkstra's, and I'm just adding a constant when I'm done. And I continue this fashion. Then I have Dijkstra's for 2, which is quite easy to solve. Are you okay? Excellent. So this is the gist of dynamic programming. This is why Dijkstra's is fast. And in math, it looks like something like this. And I can't read it, but I can't really pronounce it. So in my lame-ass attempt to write in the same thing, if I have a group of node A to F, I know the optimal solution would be B to F plus A, or just B to F. So either A would be part of the optimal solution, or it won't be. Kind of makes sense, right? And then I have just 2 problems to solve. Or just 2. I have 2 simpler problems to solve instead of 1 big. And in a more mathematical way to saying this, I tell you there's an optimal path from I to J. And let's imagine another node K just before I and J, just before J. And it's easier to solve the optimal path from I to K and then just add on J. And this, rinse and repeat, and you have a problem of 1, which is simple to solve. This is the gist of dynamic programming. And I gotta do a quick pause here. I mean, I have been showing you a lot of arrows, a lot of number, a lot of math. And I'm gonna leave that part behind for a while and just talk about theory. And yes, this has been the practical part of my talk. Now I'm gonna move on to theory. I will tell you the easiest way, or no, I will tell you the hardest way to win $1 million. And this is no joke, this is actually very true. You get $1 million. You will get $1 million if you solve this thing. How many of you know about time complexity? Excellent, excellent. So the algorithms I described has a time complexity of big order 1, or order n, or big O notation of n, which mean they're linear. Time complexity basically it's measurement how long time something takes, and it's not related to CPU power, it's related to how many iterations in a loop you're doing. So the breadth first search is basically searching the full, every node. That's why it's have order n, which also means that it takes twice long time to search a graph of 100 nodes than it takes to search a graph of 50 nodes. And as you can see, the depth first and the greedy algorithm basically have the same time complexity. This is the theoretical worst case scenario. And I told you Dijkstra's was quicker, but obviously it has a worse time complexity because it's on my slide. And this is, like I said, it's the theoretical worst case scenario, but Dijkstra's has a way better average. That's why Dijkstra's is quicker. We only been looking at the problem of find the shortest path, right? And that is a simple problem to solve. But what if we modify it slightly? Say we have a problem to looking at the shortest path using all the nodes. The best algorithm we got for that kind of problem is Bellman held carp. And that's time complexity is n to the power of n times n to the power of 2. And that's awfully slow. I mean, your mind should be like, that's so slow. If you didn't go like that inside your head, I have a very scientific graph to show you. This is linear time complexity or polynomial time complexity. Over here is the exponential time complexity, and it grows so quickly. And now to the million-dollar question. It's believed that these kind of problems you can solve in polynomial time, there are one group of problem. And the kind of problems we only can solve in exponential time or factorial time, there are another group of problems. And we believe, like we the society believe, that these are two separate groups of problems. However, we are not sure. We don't really know if they are separate or not. Yeah, okay. And having these problems called P and these problems called NP. And we think NP is not the same as P. So, sorry, I really need my notes. So, if you can prove that these are separate groups, or if you can prove that these are the same groups, then you will get $1 million. Which basically means if you can come up to a quick algorithm to solving one of the NP problems, then you're rich. So let's try to investigate a little bit. One of these problems in NP is the traveling salesman. It's a TSP problem. You probably heard of it before. You're gonna, like I mentioned, you have a group of cities, and you're gonna find the shortest path between the cities. So say you're a traveling salesman, you're gonna visit Amsterdam and Paris, and you're gonna visit Stockholm and Moscow. You shouldn't go from Amsterdam to Stockholm to Paris to Moscow. Yeah, you figure out. I mean, you shouldn't fly back and forth, right? You should basically fly in a circle somehow. And that's the problem. And yeah, find the shortest route, that's the problem. So you could ask yourself, isn't Dijkstra's, which is finding the shortest path, isn't just TSP an edge case of the finding the shortest path? So couldn't you just modify Dijkstra somehow? And you really can't, because Dijkstra is meant for finding the shortest path, not using all the nodes. But what if we started using all the nodes? Like we require a length of the solution. Then you run into issues with duplicates. I mean, the shortest path might have a duplicate. So what if you modify Dijkstra not to allow duplicates? And this is where it gets tricky. This is where scientists almost crack this problem, but it doesn't really work. Because if Dijkstra is finding a shortest path from I to J, it's assumed it's a K, as we know. And then we're going to try and find a shortest path from I to K. However, Dijkstra cannot guarantee that J is not within that path. So you will have duplicate that Dijkstra would never find. So in order to solve this thing, you need to remember not only where you came from, but you need to remember the full chain where you came from. And doing that modification to Dijkstra means that Dijkstra got a worse time complexity again. So no, you cannot use Dijkstra for solving TSP. However, though, this thing can solve TSP, and very efficiently. This is a bee. It weighs about 1/10 of a gram. Scientists have discovered that it's perfect solving the traveling salesman problem. What they basically did is they created a graph like this with H is a hive and all the A, B, C, D is flowers. So if you didn't know, a bee, every day it goes out to hunt of food, so we're visiting all the flowers and then get back to the hive. And doing that route is always take the shortest route between those flowers. So when scientists have the flowers like this, it took the shortest route. But then when they move the flower, when the bee discovered that the flower has been moved, the next time they did the route, it again took the shortest route. So this bee solved a problem that our supercomputers can't, which I find quite amazing. So you may ask, like, hey, why do I talk so much about TSP? TSP is a simple problem to explain, but it's very, very hard to compute. And I can tell you TSP is an NP problem. And I can tell you that there is a way to convert one NP problem to all the other NP problems. So it means if you find a solution to this simple to explain problem, you can convert a solution to solve all the other hard problems we know of within reasonable time. Another of these NP problems is called the integer factorization problem. And if you read some security protocols, they often start with saying, choose two very large primes and multiply them together, and that's your secret key. And that key is secret, or that's the key is secret because computers have a really hard time factorizing integers. So it basically means, again, if you have an efficient solution to TSP, you can efficiently brute force all our society's encryption. And you can say, oh, but what if we just increase the encryption size to 2,000 and whatever? Like, you can efficiently brute force that as well. One other of these problems in NP is the satisfaction problem, SAT. And that's the problem that Composer is solving when you do a Composer update. So you say, here's a list of my requirements, and the requirements has requirements, and Composer is trying to figure out which version to install. And if you think Composer is slow, it's because it's trying to solve a problem that are the hardest problem we know of. Also because network latency, but mostly because it's that thing. So let's try. Like whenever I was in university and I have a professor that told me this story. We talked a lot about NP problems, and he said, "This is the hardest problem there is. Blah blah. You can't solve it in a reasonable time." So I'm like, I'm pretty smart. I will solve this. So I obviously I'm trying. I'm up for the challenge. So this is what I did, and this is what I will do with you. Let's consider this TSP problem of 5. Again, I removed all the numbers because they only make things complicated. The ideas will still be the same. I have 5 options on where to start. And I randomly choose the H because that's a good start. Now I have 4 options which node to go to next. And I choose the B. And then I have 3 options, 2 options, 1 option, and then I go back to the start. Now I'm calculating. If I calculate how expensive it is to do this route, I'm calculating 1 route. And as you may have noticed, there's more routes, and I have 5, 3, 2, 1 options, which means like, hey, maybe this is factorial, right? So I gotta calculate n factorial, or 5 factorials number of iterations here to find to know which route is the shortest. And 5 factorial is, obviously my algorithm is awful because it's n factorial. And to really get you an idea of how awful factorial is, 5 factorials is 120. 15 factorials is 1.3 trillion. I got a semi-fast computer. If I wrote this algorithm and tried to solve TSP, I maybe could solve a TSP of 20, 25. Not larger than that. And yeah, 2025, not larger than that. It would still solve, but it will take literally forever. So let's apply our dynamic programming skills here. Let's do something better. Could we find some subproblems and calculate the optimal route of the subproblems? Yes, of course we can. It's the correct answer. Excellent. So I take this subproblem. I calculate the optimal route here. And then I take this subproblem and calculate the optimal route. And that subproblem and this subproblem and calculate the optimal route. And when I've done this for a few times, I can take the partial calculations and I can add them together and semi-figure out the optimal route without calculating everything. Without calculating all the subproblems, I can figure out where to calculate and have a slightly better algorithm. Kind of like Dijkstra is not looking at all the nodes. Oops. So with this trick, I can get down to this time complexity of n to the power of 2 times 2 to the power of n. And this is called the Bellman-Held-Kalp algorithm, which was 3 amazing mathematicians that didn't come together. I think 2 of them worked together, and then the third one just shipped in a little bit. And they came up to this, which is amazingly better, but still awful. I mean, on my computer, again, with this algorithm, I can maybe solve a TSP of 35. And imagine like how does Google work? I mean, if you were looking for the shortest trip in a country with more than 35 cities, how does Google do it? And Google has other tricks. That's a sidebar question, but I'm saying this is why this is a hard problem. This is why our security protocols are safe, because this is so difficult to solve. So, I hope I've showed you a little bit, but it's way more than programming than just printing out information on a website. Like, if that's the only thing your company is doing, maybe this thing is not really for you. But however, if your company is doing something cool, like you're showing the best restaurants, or you're matching people and companies back together like I am, or maybe you show some kind of score on a picture, then yes, you should definitely look into graph algorithms and graph theory. And dynamic programming is the way to make your algorithms performing better. Thank you from me. Do you have any questions? One good question might be, why is it called dynamic programming? And I just found out this the other day. It was back in the 1950s. There was Bellman, Richard Bellman, who made this fancy algorithm. He was working in the US Air Force as a mathematician, and they elected a minister of defense. And that guy, his name is Wilson, and he hated the word research. This is words from Bellman. And Bellman says it wasn't really an exaggeration. His face got red when they mentioned the word research, and he got angry. And Bellman was working as a mathematician, and basically this was this boss's boss. I mean, how could Bellman defend what he was doing? So he was working on a multi-step processing decision management or something, very mathematic. So I gotta find a new name for this. And that's why he chose dynamic programming. A word that doesn't really say anything, but still says a lot. Yeah, it's all because we have politicians who hate science. Do you have any other questions?
How do I contact this? Do tools like Neo4j help you solving such problems?
If tools like Neo4j help me solving this kind of problems, Neo4j is a graph database that has recommendation algorithms. You can basically say, here are everything I know. What would you recommend me? Or what other has bought and stuff like that. Neo4j is using algorithms with dynamic programming. Yes, I'm sure they are, because they have very efficient things, and yes, they help you with it. Yeah, I gotta stop there. Yeah, I'm sure they are. I'm not 100%, but I'm sure they are, and yes, they help you with it. So this is hidden in the database itself. One other question over there. Oh, that's a little bit out of topic. What's the benefits of an index database compared to a graph database? When you say index database, you don't mean indexes. You mean like a Neo4j, a graph database. Yeah, sure. So I've talked about graph algorithms. That's why we have a question about graph databases. What a graph database is good at is queries where in MySQL would be plenty of joins. So if you ask like, hey, I want to find all the people in Stockholm that like beer and programming and has a dog. And doing that join with a table of millions will be impossible in MySQL. In Neo4j or Graph database, that's a quick question. That's a quick query. If there's not any more questions, I've been happy that had your attention for almost an hour. Thank you.